I feel like, did you guys ever hear that song, Ice, Ice Baby?
Yes.
Ice, ice. Yeah, we should play that because I am bringing you into the world of ICE tables today. Okay. ICE stands for Initial, Change, and Equilibrium. Now, if you have been with me in the past for rice, or I'm sorry, if you've been with me in the past for BCA tables, ICE tables, sometimes they're called rice tables because you have the reaction up here. Okay. They work in a similar fashion. So if you understand BCA tables, this isn't so bad. Okay. Now, one of the things that you have to be aware of with this is in some of the problems that we give you, you may need to use the quadratic equation. But on the actual AP exam, there will be no situations where you have to use the quadratic equation. However, if you have one of these nice fancy calculators, there is a program that you can put in here, and we can copy it over for you, that will do the quadratic equation for you. All you have to do is enter the values for A, B, and C, hit a button, and it solves it for you. It is a work of sheer mastery and wonder. Okay, so if you don't have that program on your calculator, you might want to come and see me or somebody else to be able to get that. I'm sure it's floating around here in several different calculators. Okay, you just need a cable that connects the two, and I've got that cable somewhere in a drawer here. All right, so like I said, this stands for, sometimes you'll hear them called rice tables, where this is your reaction. This is what you're starting out with initially. This is what's happening. Either you're taking some of this stuff to form this, or you're taking some of this to form these, and then how much you're going to be left with at equilibrium. Okay? So, if you're given these initial concentrations at equilibrium, we're trying to figure out what the Kc value is. So if we're trying to figure out Kc, that is our constant at equilibrium. So we've got to solve for this box and then use those concentrations to solve for Kc. Does that make sense? So first step, make sure that your reaction is balanced. This is our kind of dividing line. They made it a little thicker here so you can kind of see the difference between the two. Okay. Now, since you have no information about the initial values of C, we assume that there was none initially present. So we're going to put a 0 there because initially, you know, a lot of times they'll say, like on your quiz, they'll say in a previously evacuated, you know, reaction vessel, these two items were added in. Okay. So if they just add those two items in, of course, there's none of that.
She said to keep these in case students need help. And
All
then we
right.
had a lot of it.
Put them on the bottom down by that bell in that basket with all the other papers. Thank you. All right. So we are assuming that. So by filling in the value for C, we can see that C must have increased by this much. Yes? Because at equilibrium, that's how much we have. And they told us that in the problem up here. Okay? So that means that this increased by 0.120 molar. All right. If that increased by this amount, and this is in a 4-to-1 ratio, how much did this have to decrease by? Yep. No.
Wouldn't it be what? It would be 4.8. I'm going for it.
What? I'm going to take this and divide it by 4 and then multiply it by 1. Remember how we do clouds?
Yeah.
Okay. Divide by 4, multiply by 1. So what is this guy here? Okay. Everybody with me so far? Did I lose anybody? Does that make sense in terms of ratios? We're making this stuff, and in order to make this, we have to use some of this stuff up. So that's why these are minuses. All right, so how much is left over? Well, here we're going to have ready to go with that? All right. So now if we want to figure out our KC value is going to be the 4C, which is this amount. What do we have to do with that?
Oh, exponent of 4.
Yep. I have to have that up to a 4. And then I'm going to divide that by
970 times 940
squared. Right. We have to square this value because of that coefficient there. Okay. So see if you can get that math to come out on your calculator. Anybody not get that on their calculator? You doing okay with your calculators? Remember, when you go down to this bottom line and you're multiplying all this stuff in, that whole line down there needs to be in its own parentheses. Okay? Because otherwise it's going to pop. If you just put this in, if you hit divide and then put that guy in, when you go to hit multiply again, it's going to pop this value up on the top line again. Okay? So be careful with that with your calculators. That's usually where people end up goofing these up, trying to get that entered in. Okay. Order of operations. All right. So that's what we did there. We plugged and chugged. Now we're going to do another one. Okay. So here we're starting out. We are provided the value of K, and we have to find the equilibrium concentration. We can also use ICE tables to solve this. They gave us our equation here. So this equation's already balanced. Okay, if you need to put an arrow in there to help you out, go ahead. Okay, we have 1 molar here, 1 molar here. They're reaching equilibrium. So when we go through this equation, this is going to be 1 minus x for equilibrium. This is going to be, we're going to minus an x2 in this column. This is going to be 2 minus x. Over here, we would have started with 0, and we're going to add x in. Okay. Can you see where we're falling into the land of quadratic equation here? All right. So let me show you a way to be able to get yourself out of that. Okay. We know that our K value is this amount. Okay. Right. So if we take our initial amount or concentration, so let's just do the 2 because that's the biggest amount. Okay, if we take that initial concentration and divide it by K, shoot, come on. Piece of junk. Every day, it's just a struggle, you guys. Every day. All right. If that is greater than 100, then you can ignore the X. But you have to document that you did that check in order to ignore that X. So you have to tell the person that's, in Salt Lake City or wherever they're at this year, you have to tell them that you're ignoring this X. And the reason why you're doing that is because this is going to make so little of a dent in this amount that it's not going to matter. Okay? Because this K value is so small, you're not going to shift this much out of the reactant side. It's favoring the reactants. I do, yep. Okay. And like I said, this is kind of like me getting on the scale and plucking a hair out. It's not going to change my weight. Now, technically did it? Yeah, but it's not noticeable. Okay. So you just have to document that you did this check. And if you did that check, then those can be ignored. And then guess what? You don't need the quadratic formula anymore. Okay.
Why is it 2 minus x?
Because we started out with 2 in the beginning. All right. So when we set this up, we know that our K value is 3.4 times 10 to the minus 3. That's going to equal our products, which are X, and we don't need to raise that to a power because there's no coefficient, over 1 times 2, right? And that is going to end up being your bottom. We don't need to raise any of those to a power because there's no coefficients. So now all you have to do is solve for X. Okay. So X is going to equal 2 times this amount. 2 times that amount is 6.8 times 10 to the negative 3rd. That's a very small amount. It's not going to put a dent in these. So your ignoring was validated. My algebra making sense to you? How about the concepts? Thought process. Some of this you just got to practice a little bit. Okay. So that's the mathy part of that. All right, let's do a couple more. Oh, wait a minute. Did we not finish that one up? Did they want us to find the values? So we found that X. Yeah, and we would just assume that that's 1 and 2, and then that is X, so that is the value for that. All right. So here we've got ICL was added to reach a partial pressure. So now we're in the land of KPs here. So we're working with pressures. We are reaching a partial pressure of 2.45 in a previously evacuated vessel. Right? After the reaction was reached, the pressure of I2 was 0.3. So I'm going to put that down here because that said that at equilibrium, I2 is 0.3. All right. Let's see here. What else can I do? Was added. Enough ICL was added. So we just had ICL in there. Okay. So that's going to start out at 2.45 for our pressure. And these wouldn't have had any pressure because there wasn't any in there initially. Okay. So we formed 0.3 of this. So we added 0.3 here. And if we added 0.3 here, and these are in a 1-to-1 ratio, what do we have to add here? 0.3, which means at equilibrium, that's going to be 0.3. What do we do to figure these values out? Okay, so that's going to be 0.6. And what am I going to do with that? I'm going to subtract it because I'm using some of this up to make this stuff. All right, and we want to solve for Kp then. Kp is going to equal 1.85. What do I need to do to it? Square it because of this coefficient. So this guy needs to be squared because I had a coefficient here. That's going to be over 0.3 times 0.3. And I should end up with a Kp value of, anybody?
308.
I don't think it's 0.3.
I got 38.
I got 38 too.
Yeah.
You good? Okay. All right. So we've got 38. Remember, no units on K values. Anybody need to know where I got a number from, how I got anything up there? Is it making sense? Like I said, if you understand BCA tables from regular chem, these that's one of the reasons why I switched over to BCA tables in honors chem, because once we get to ice tables, it's like, oh, we can fly through those. There's no explanation. Like, you just get it. It just is intuitive at that point. All right. We do. What do we do? What do we do? First, we write our equation out. And look at that. That was so nice of them to balance the thing ahead of time for us. They do that a lot in AP because they figure if you're in AP, you should be able to balance an equation. So they're not going to test that. They figure you should know how to do that at this point. I'm not so hot with drawing straight lines on this thing. There we go. A little bit better. All right. Ice, baby. Okay. We have the reaction mixture initially contains a partial pressure of NO2 of 0.1 atm. So I'm going to put that right here because that was my initial pressure. When it's reached equilibrium, the partial pressure is now at 0.08. So how much did I lose here? 0.02. So how much did I gain over here? 0.01. Because this is in a 1 to 2 ratio. So at equilibrium, this guy is going to be 0.01. So Kp equals 0.080 squared divided by 0.01. Not squared, because there's no coefficient there. Let's see if Presley can redeem herself.
0.64.
0.64. Very good. All right, you good? Ready to move on to 7-8? That's why 6 was upset, you know. It's 7, 8, 9. I know, it's bad. I just told a really bad joke.
Hi. Can I get your signature?
Mine?
Yeah, for Key Club.
Key Club. Oh,
Yeah.
don't mind interrupting my video for this.
Oh, thank you.
All right, here we go. We can have representations of this equilibrium as well. Because what's life without representations? So they enjoy quite a bit, giving you these particle diagrams where you're given initial and then you've got your change because they're adding some stuff in, and then your new equilibrium is established with more stuff in there. So sometimes they'll do that. Okay. Make sure that you are considering states of matter here, relative amounts. So if you started out with 1, 2, 3, 4, 5, so 2, 4, 6, 7, 8, 9 of these blue guys, and you added some more in, so 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Make sure you've got the same amount over here after that addition for all the stuff, because they'll nail you on that. Okay. They also can do this as a graph interpretation as well. Okay. So typically this is what that's going to look like, where you have your A and B and then AB over here. So if we look at that equation, I may have to make this a little tinier so we can get everything on the screen at one time. Okay, so here is my equation for A. Okay, so here is A, and they're adding in AB3. So they're adding in more of this stuff. So if they add in more of this stuff, then more of this stuff is going to form because of that to establish equilibrium. Because if this is at a higher amount, this stuff has to be created to be able to get that back in balance. So that's why this is kind of a subtle curve here. This is also a subtle curve, but it's bigger, a bigger curve than this one. Why is this one so much bigger? There.
It's 3 times the amount of
Right.
B.
Yep. There's 3 times the amount of B than there is A. So that's why that's bigger, because more B is going to be formed than A. Now, do you see the distinction between these subtle curves where this is, happening kind of slowly versus an abrupt change here? Why is this change abrupt and then subtle, and these are just subtle? Right. We added this stuff in. So we just dumped a whole bunch of stuff in there of this, Okay, we dumped a whole bunch of this in there, so it went up really fast. Why is it going down instead of going up like these other two? Right, we're using some of that up to form these other things to get to equilibrium. Okay? And that's just essentially what the verbiage down here is talking about, is what I just went through with you. Okay? All right, let's see how much of this we can get on the screen. Not enough, really. Okay, well, we can get started here at least. Okay. This requires a little stretch here. Another sip of coffee. Okay, we are in the land of moles here. See that? And we're in a 2-liter container. So they want to know down here. Remember, ice tables are using either molarity right now, or they are using pressure. Okay. So our initial molarity here, we had 6 moles of nitrogen, 6 moles of hydrogen, and 6 moles of ammonia at equilibrium. That was in a 2-liter container. So what is my molarity then? Three. Yep. Okay. Is that what I want to use though? Or do I want to stick with moles?
Just as the number of reactants and products.
Oh, number of reactants and products. Okay, fine. Okay, so we do have 6 of everything here. So they just want us to put that down here on here. All right. When we go through the change here, we end up with 5, 3, and 8. And we could sit there and count them if you want, but hopefully you just trust my math. All right. Oh, you guys were supposed to draw this in. We weren't supposed to give that to you, were we? Did you get given this? That was nice of me. All right. All right. Let's look at the we do then. So here we're given 6 moles of nitrogen, 6 moles of hydrogen, and 6 moles of ammonia at equilibrium in a 2-liter container. They want us to sketch the graph showing the amount of reactants and products that will change in the container if it was reduced to 1 liter. So if I start out here, I have my equation. I'm going to just do some stuff up here so you can see what I'm doing, all right? So N2 plus 3H2, 2NH3. We are starting out with 6, 6, 6. Ugh. I know, it's bad. See if we can change that. I didn't write the problem. Get out your pentagrams. Anything. If we're reducing this, we want to know, we got to figure out which one of these things we're going to use up. Okay, so we need to talk about how we know that the reaction is going to shift to this direction. Okay. Do you see over here in this side of the reaction that I have 4 moles of material? 1 and 3. That's 4. Okay. If I reduce the size of this container, my equilibrium is going to shift in this direction. It's going to form more of this stuff. Why do you think that would be?
More, it's closer together, so more of it is more likely to collide and react.
Okay, yep, it's closer together, so we're going to react with these. But why wouldn't this form back over to here? Why would we go this direction and form more of this stuff instead of the other way?
Because there would be less molecules, and since they would be hitting together more, they would be forming more molecules.
Right. So when we make our container smaller, it will shift to form fewer molecules. So if I make it smaller, it's going to shift this direction. Now, if I made the container bigger, it's going to shift the other way because it's got more room now. Okay. So it's going to take 4 moles and make 2 moles out of it. So it takes up less space. Okay. So that means that we're going to be using up this. We're going to be using up this, and we're going to be making this. So in terms of our line here, we're going to be increasing the amount of this stuff. How do I do that? I'm not good at drawing, you guys. We're going to be reducing this stuff. This is the H2, so this needs to be about the same amount there, but just go in the opposite direction. And then this one is going to reduce just a little bit and be, oh, that's not a very good line, you guys. I'm sorry. There, that's better. Nope, no, it's wrong. What's wrong?
Is that the problem reducing the pressure?
Is this pressure?
Or volume, sorry. The volume is being reduced.
Yeah, the volume's being reduced. Oh, so the pressure would increase. I was doing moles here. I wasn't doing pressure. Riley's right. Let's try this again. Thank you. You guys are so smart. This one will still be the same. So I'm okay there. Yeah, I'm sorry. I was in the land of moles, not the land of pressure. Thank you for calling me out on that. All right, so this one is going to be going up as far as pressure, and then the pressure of that's going to be reduced down a little bit because we're using some of that up to make this. And then this guy, oh, but that'll be more. Wait a minute. That's my H. They've got this kind of backwards. I want the N to be there instead. All right. So this is going to be kind of abrupt with the pressure, and then it's going to come down a little bit higher than this was. Okay. That's 3 times. This was 2 times. And then this guy will go up. And then he's just coming down a little bit, but not much compared to that one, because that's just 1x. All right. Hopefully I have led you to the right place. If you want a better explanation than I've provided, obviously, maybe tune into the video. Feel like a Monday to anyone?
Yeah.